Okay, we can get started. So as you can see, I don't have a slides today, so we're going to keep talking about GPU architectures. And today it's our GPU architecture 3. And this should be the last lecture for GPU architectures. Then like for 3 lectures, it should be in general good enough to introduce how GPU works in general. And in the first lecture, we talk about how a GPU program is written and GPU assembly. Then in the second lecture, we talk about the GPU core architecture. So how GPU performs computation, how those instructions are executed. So in today's lecture, we're going to mainly talk about the memory system and how the GPU memory system works. Then the GPU memory system is actually rather simple, not that complex. So I don't really need 1 hour and 20 minutes to talk about the whole GPU memory hierarchy. But so let's start slow now with some review about how the computational part works. Then starting from there, we go into the memory system. Okay, so we start with the compute unit architecture. What are the components in a compute unit architecture? So this is a compute unit, or called CU. Then in NVIDIA terminology, this is also called streaming multiprocessor, or SM. Okay, they are basically the same thing. A GPU SM is slightly more powerful than AMD compute unit, but they're still anyway rather similar. Then in the front end of a compute unit, I want to leave a little bit space. Then in the front end, we have 4 groups. Now we call them wavefront pools. Okay, and there are 4 wavefront pools per compute unit, and in each wavefront pool there are 10 wavefront slots. Then pretty much in all the GPUs I have done, there are 4 wavefront pools per compute unit, but this number, the number of wavefront slots within each wavefront pool, this is a variable number. In some low-end GPUs, it can be a number of 8 rather than 10. Okay, these are some configurable number. Then, so those are wavefront slots. Then we can assume that these wavefront slots are being occupied, right? So there are basically 40 wavefronts sitting there and waiting to be executed. Okay. Then before this instruction can be executed, we need to first fetch the instruction. So the first stage of the pipeline is fetch. Okay. So this is a fetch arbiter. A fetch arbiter determines which wavefront can fetch instructions. So it can determine which instruction can fetch instructions with thumb rule. And after that, this is an issue arbiter. And before the issue arbiter, we call this part front end. And we call the rest of the pipeline back end. So back end is responsible for executing the instruction. And the front end is fetching the instructions, storing there, and waiting to be executed. And they're decoupled by this issue stage. Okay. Now, where this instruction can be issued, there are basically 5 major units. The first unit is a branch unit. Right? First unit is a branch unit. Then we have a vector mem unit, vector memory unit, and there's a scalar unit. I should put scalar unit on top. Scalar unit on top. Then if you check the AMD assembly, both branch instructions and scalar instructions, both of them start with an S prefix. So they are both scalar instructions. And also, they are both integer operations. So branch is an integer operation that only calculates the PC, right? So it's an integer operation. And scalar is also the same. So scalar is integer only operation. So if you need to perform some floating point operation, you have to put it into the vector. Although even if you are doing the same operation for all these 64 threads, you have to put it to the vector part. Okay, because scalar, both the scalar units does not equal floating point operation units. Okay, so those are rather small components, like in terms of die size and energy consumption. And also, if you compare with the vector instruction or vector ALUs, then the computational power of this one and this one can be ignored. So that's why when we're calculating the computing power of a GPU, we do not even consider these two. Okay. Then we have a VMAM unit. Okay. After VMAM, we have a LDS, local data share. That's something we're going to talk about today. Then at the end, let's draw it in this way. Let's draw from like bottom input, okay? We have 4 unit called SIMD unit. SIMD1, SIMD2, SIMD3, SIMD4. Okay, so if you check the AMD official documentation, you will see they call this thing SIMD unit. They also call this thing wavefront pool. They also call it SIMD1, SIMD2, and so on. Okay, this is in the official documentation. So what does that mean is the wavefront that are being allocated on this wavefront slot can only go to SIMD1. And this wavefront can only go to SIMD2. This wavefront can only go to 3, and this can only go to SIMD4. So if you understand it in a more NVIDIA style of like how NVIDIA draw this diagram, NVIDIA has a concept called subcore. Okay, so what is a subcore? In NVIDIA, they typically draw this thing in this way. This is an SM. Okay, within each SM, there are 4 subcores. Subcore, right? So there are 4 subcores in NVIDIA architecture. So if you compare with this diagram, now basically this SIMD and this SIMD, they are pretty much one subcore. Okay, but AMD just have more resources that are shared by these subcores. So for example, the fetch arbiter is shared, issue arbiter is shared, branch, scalar, vector, memory, LDS are shared by all these AMD components. So that's why AMD prefer to draw this type of diagram in this way rather than that way. Then there's definitely a shift after the RDNA age. And we slightly talk about the RDNA difference, hopefully by the end of today's lecture. AMD is also shifting towards more and more like this style, but let's still learn the classic AMD architecture is basically implemented in this way. Okay, so in each SIMD, then SIMD are a group of ALUs, right? The arithmetic logic unit is where this calculation can happen. So combinational logic here. Now within SIMD, there are 16 lanes. We call them lanes. So basically 16 ALUs that can perform 16 operations per cycle. When I say 16, these 16 lanes, we refer to single precision floating point lanes. Okay? So then for this one, this is standard for any GPU. This is a standard GPU, at least if we go back a few years before. Like these days, probably AMD will start to build GPUs specific for LLMs. So even NVIDIA, if you look at their low end, you know that NVIDIA is selling those desktop this big, like personal LLM computers, right? So why those computers can build those that small, but can still do very high performance computing, can still do LLM, because in those GPUs they do not have FP32 operation. They only have FP4. Okay, floating point, 4-bit floating point numbers. They only have this low precision calculation. That's why they can do such a high performance computation. But for a regular GPU, you cannot really only rely on FP4. So for most of the time, like in a classic understanding, the raw power comes from floating point 32 operations. Okay, single precision. Then, if this is not a configuration, this is by standard, right? Some other configurations. So for other precisions, it's a parameter that can change from GPU to GPU. For example, FP64, double precision. What's the power of FP64? It can be from 0 to 16 lengths. Okay, so what is in 0? So for some gaming only low-end GPUs, they will have only 0 lengths, no lengths at all. So they don't care about double precision operation, right? Then, so rather standard is there may be 2 of them for regular gaming GPU. They reserve some capability of performing double precision operation, but not much. We can barely do it, but don't expect too high performance. Then some others may have 8 or 16. What are 16? For example, those high performance computing, MI300. I don't really know what exactly is the number in MI300. But those super high-end professional professional compute-oriented GPUs, they tend to have 16 lanes. Okay. Then we can talk about FP16. So in early ages, it's 16. Then as FP16 is getting more and more important, it's growing to 32 lanes. And today we're adding more FP8 and FP4 support, and they're likely to have something like doubling the number of lanes as we go down with the precisions. Because if we have a smaller precision, the die size area is smaller, right? So if we build a GPU today, high-end computational only GPU, very likely we'll build something like FP64, then we'll have something like 2 lanes, 2 to 8 lanes. 32 will have 16 lanes. 16 will have 32 lanes. 8 will have 64 lanes. Okay, this is very likely to be what's the case for modern GPU. So double the calculation capability as we go down one level of precision, as we have the precision. Okay. So those are the lanes. For AMD GPUs, I don't have clear evidence that they can do concurrent calculation, out of order calculation. So this is a typical interview question for hardware design or for GPU architecture. If you go to a company like AMD or NVIDIA, they may ask this type of question. What are the possible hazards in GPU architecture? At least in a classic understanding. Okay. What are the possible hazards? So when we talk about hazard, immediately we should consider read after read, read after write, write after read, write after write, 4 possibilities, okay? Read after read is not a problem. We can read any times we want. What about read after write? In what case we can have read after write? Read after write happens when we have a pipeline, right? We have the first instruction is a write instruction, and the second one is a read instruction that needs to read from that one register. So for example, this is V1, and this one write into V1, and this one read from V1. Okay, this is a read after write problem. So can GPU have read after write problem? Then, so if we don't do anything, if this issue arbiter works exactly the same way as a CPU issue arbiter, it should have, right? But it doesn't work in the same way. Let's talk about this hazard. Like before we talk about how this issue works. So write after read. Write after read and the write after write, they both need, say, 2 instructions to go onto different paths, right? So can we have different paths? Yes, we can have different paths. For example, scalar can go much faster than a vector, right? So this vector, we're only talking about something like floating point operations. Now we're talking about floating operations, we're talking about add, multiplication, those rather regular operations. And you also need to consider sine, cosine, log, this type of non-standard operation. Those can take a very, very long time, okay? So in that case, these 2 types of hazard can also happen. So how GPU issue arbiter handles this problem is basically in this way. So this issue arbiter will check the status of each wavefront, okay? If this wavefront already has 1 instruction that is currently in the pipeline, we cannot issue from there. Okay? So let me say again. If this wavefront has 1 instruction probably here in the pipeline, right? If that wavefront has 1 instruction that is here, that is currently in the pipeline, the issue arbiter will never issue another instruction from there. Okay? At least this is how the classic AMD works, AMD GPU works. So if this can guarantee, so basically from 1 thread, it's impossible for 1 wavefront, it's impossible for 2 instructions to be on the pipeline. Now, if that is the case, if you consider from the perspective of 1 wavefront, it's not a pipeline execution. It's a single cycle execution. If it's a single cycle execution, there's no read after write, and there's no write after read, and there's no write after write. Okay? Impossible. Okay? So this is only for classic AMD GPUs. Now for NVIDIA GPUs, I know from a very early stage, this is not the case. NVIDIA has this double issue. Why? NVIDIA wants to take the opportunity of say, oh, I have an integer pipeline, right? I have integer unit. I have floating point unit. Oh, then I have an integer instruction and a floating point instruction. Now I can use the pipeline at the same time to improve the performance. Okay, so AMD only rely on to find another thread that may be able to occupy another unit to improve this parallelism. But NVIDIA also tries to find the opportunity from 1 thread to explore these opportunities. Okay, so NVIDIA has multi-issuing from one warp. AMD in classic architecture, it doesn't allow that. Okay. So the very common misunderstanding is context switching. So when we say context switching, like it's in the GPU context, then we mean in a CPU context. When we say CPU context switching, a CPU core can only execute one thread at a time, right? So context switching means we need to store the context into the memory and load another thread from the memory to start to execute the other thread, okay? So switching from one thread to another thread associates with overhead. Then the quick question is, what is the context switching overhead for GPUs? It's another good interview question for architecture. Then the quick answer is there's no overhead, zero overhead. Why? Because if we do not consider it in this way, just consider it as a pipeline, right? Just simplify as a pipeline. Remember, we say we never have one verb or one wavefront to have two instructions in the pipeline. But the pipeline can still be full. How it can be full? It's full in this way. This is for wavefront 1, for verb 1. And in this slot, we're actually executing another instruction from wavefront 2. Then this is wavefront 3, wavefront 4, and wavefront 5. So in CPU, what's happening is this is from T1, thread 1, this is from thread 2, this is from thread 3, thread 4. No, it doesn't work in this way, right? I don't know why I'm writing this way. In CPU, how it works is different instructions from T1, 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 T1. T1, not T2. Right? In CPU, this is what's in the pipeline. There are different instructions, but definitely from one thread. This is the GPU way. There are different instructions, but from different wavefront or different verbs. Okay? So context switching is happening every cycle. Right? So that's why context switching in GPU is overhead free. There's no overhead for context switching in GPU. Okay? So switching from one verb to another verb happens at every cycle, so there's no overhead. Any question?
I think for all these wavefront, does it mean they are executing the same code block?
Okay, for different wavefront, are they executing the same code block? So if you are writing a kernel, let's say, I think what you mean by code block is basic block. So the quick answer is no, they are not executing the same basic block, but they are executing the same program. They may execute the same program. So they say, if you have a kernel, right, you write a kernel. So typically a kernel is not super complex, but some kernels can be really complex. So all the way front, let's only assume one kernel is executing there, okay? So all these threads, all these verbs are executing the same program, the same function, the same kernel, okay? But they may have very different progress. Some may be have been running for a very long time, like in 100 iteration already, while the other verb may just started. Okay, so they have different progress, but they're supposed to execute the same piece of program.
So for this that each walk always goes through the fetch instruction and the pipeline. they go through this, or they have some sharing, instruction if they have.
Okay. So is there any sharing in the instruction? The quick answer is from the CU level, no, there's no sharing. So each one needs to go to sharing, goes to the fetch and issue. So there's no quick way to do, well, at least at this stage, I don't want to go too fast, but at this stage, just consider each wavefront is totally independent. Okay, so if you talk about sharing, or like how we can reduce the overhead of fetching, fetch is connecting to L1I instruction cache. Okay, so the fetch arbiter is connecting to L1I cache. L1I cache is super fast, and what's the likely hit rate? It's pretty much always hit, other than the first time miss, right? Other than the first time, it's pretty much always hit. So it has something like 99.9% of hit rate, right? So if this is like 1 cycle, 2 cycle latency, it's not a big problem. It can pump instructions very quick. And in AMD design, each L1I can provide 4 blocks. Like this block can be something like 32 byte, okay? So it's pretty quick. You can pump instructions back to the core pretty quick. In some corner cases, instruction fetch can be a performance bottleneck, but most likely it's not. Okay.
So if there are some control divergence between the wall in the same CU, so it will load multiple L1 can
We will load different cache lines. If these verbs are executing different parts, yes, they can access different instruction, different addresses in the instruction memory. Okay. So quick answer is here. The context switching in GPU is overhead free, and then it's always happening. Okay. Then let's quickly talk about another concept, is latency hiding. Latency hiding. So latency hiding for both CPU and GPU, latency hiding is necessary. What is latency hiding? Is basically say your memory is slow. It takes probably 100 cycles to get the result back. Then your core shouldn't stay there and wait for 100 cycles for the memory to return, right? And so this is the memory operation. It takes this long time to execute, right? Now, if we don't hide the latency, we'll wait until it's finished and execute ALU operations. ALU operations, right? This is a case for no latency hiding. And this part is the latency we're referring to. Okay, so how we really want to hide this latency. We don't want this latency to dominate the execution time. So the quick understanding is to move this ALU or to move some part of ALU to the front so that we can execute in this way. Now, when the depending, say this is actually the depending instruction. Now you can immediately execute after this memory returns. Okay, this is called latency hiding. Then in CPU, how we can handle latency hiding is basically by looking for instructions from the same thread, right? And use the pipelines to hide the latency. Now in GPUs, how we can do latency hiding? The idea is basically we have so many threads waiting there. If one thread is waiting for memory and cannot move forward, we can select from other wavefronts. We can select from other wavefronts in the wavefront slot, wavefront pool, to execute ALU instructions to hide latency. So when this memory returns, maybe we can already start to execute our program or instruction. Then for the rest of time, where we don't let the ALU to stay idle, but we're letting the ALU to run something useful. Okay, so this is latency hiding, and the idea of CPU latency hiding and GPU latency hiding is totally different. So CPU mainly rely on instruction level parallelism, or ILP, instruction level parallelism. And for GPU, we typically call it either data level parallelism, DLP, or thread level parallelism, TLP. Okay, so they rely on different parallelism from the program and from the application, from the nature of the problem, to find opportunities to hide the latency. And you can see CPU is how hard it is to exploit the instruction level parallelism, right? You need careful compilation, careful hazard handling, and register renaming to be exploiting instruction level parallelism. And also, it's very going against the human understanding, because when you write one thread, you're expecting it to execute line by line, right? But for data parallelism or thread parallelism, when you are writing two different threads, you know these two threads will be executed in parallel, right? So it's much more easier and for the programmer to come in and to say, oh, I want it to execute in this way, to be parallelized in this way, rather than all hardware control, right? So there's always a dilemma. You always want to make everything transparent to programmer. The programmer writes super simple program, like programmer can always write Python program, but can get CUDA performance. That's the best, but it's very hard, right? Because if you write a Python program, the program itself and the hardware knows very little about the intention of the programmer. So if programmer can express more intention into their program, they have to use more complex program languages and take more effort to write the program. So there's always a dilemma. So the more complex the program language, the higher performance, right? The simpler a program language, the lower the performance. That's a general trend, although there are some outliers. Okay, so finally, we can talk about the memory. So vector memory. I'm saying this is a vector memory. You always need to be careful. This vector memory actually also need to go through SIMD unit, then go to a vector memory unit. So because it needs to do some address calculation, you still need a SIMD unit to do the calculation. But since AMD on their official document is written in this way, then I will just take it, draw it in the same way. Okay. So, but what's in the vector memory unit? The most important thing is something called a coalescer. Okay, a coalescer. So a coalescer, if you spell this word in like Microsoft Word or Grammarly, it will typically treat it as a misspelling, because this is so rarely used. The word is not in the dictionary. So it comes from the verb form of coalesce. What is coalesce means we combine different operations into a smaller one. As we're talking about MSR, we already have been talking about a coalescing effect, right? So what is the coalescer in the vector memory unit? It's like this way. Remember, this is a vector memory unit. So in AMD GPUs, that means we're actually loading 64 different addresses, right? So let's make it simple. We don't want to draw that many. So let's say a very common case, the first case, is if we're loading 0x40, 40, 40, 40. So all of them are loading the same address. How many memory transactions we need to generate? We only need to generate one, right? So all the threads are actually loading the same address. We only need to generate one transaction. So this going from 64 operations down to one instruction, down to one transaction, is the perfect coalescing. It's the best coalescing as we can expect, right? So the fewer transactions, the better. But we cannot always expect these good cases. So let's say what is case 2? A more common cases is we have a regular stride. So what is a regular stride? This is loading 0x40. This is loading 0x44. Then 48, 4c, 50, and so on. Okay? So what is case 2 here? There's a term here they call it stride. So it's like walking. How large is your stride, right? Is that by 4 byte or 8 byte or 16 byte? This is the stride. Now our stride is 4 in this case. Then we also need to know how many bytes that each thread wants to read. In this case, it's very likely to be 4 bytes in each thread. Okay? So there are 64 of them. So how many bytes are we reading? It's 4 by 64, right? For each of them are reading 4 bytes, and there's no overlap. So we're reading 4 by 64. That's 256 bytes. Assuming 64 byte cache line. How many cache lines are we reading? 4 cache lines, right? So we're reading 4 cache lines. So how many transactions we need to generate? Yeah. So remember the core and the L1 cache interface. The data bus is typically a cache line size, right? There's that many of wires, So we need to generate 4 transactions. Okay. 4 transactions. That's pretty good. We're reducing by 16-fold, right? By 16 times. We're starting from 16 transactions if we don't do coalescing. Then after coalescing, we only need to send 4 transactions. Okay. Let me erase this part. SIMD doesn't matter for memory, so I can use this part of the whiteboard, the blackboard. Okay, so let's look at K3. Then, let's say if we have a memory, or if we have a matrix, and the matrix is organizing in this way. This is a column measure, right? So 0x, so address 40 is here, 44 is here, and so on. This is called column measure, right? I always confuse with which one is column measure, which one is row measure. But this is row measure, okay. No problem then. So the idea is, if our stride is going this way, so adjacent thread is loading this part of memory, right? We can coalesce, no problem. Then the coalesce is case 2. Right? I'll call this standard. This is perfect coalesce. This is standard coalesce, right? Then in this way, if our stride is going this way, this is standard coalesce. Then if we have another way of accessing. If we have to access it this way, this is common, right? Think about matrix multiplication. On one side, you need to load in this way. On the other matrix, you have to reload in this way, right? So on matrix multiplication. So if you have another thread that is loading in this way, and let's say the length here is 4 kilobytes. I'm just making up this value. So 4 kilobytes means this matrix horizontal dimension is 1024, right? Not a super large matrix. It's a reasonable size matrix. That means here we're accessing 40. Now here we're accessing 4K by 40, 4K plus 40, 8K plus 40, and so on, right? So every address differs by 4K. So this is the address that we want to access. This one is accessing 4K, 8K, although there's an offset. This is 12K, and so on. Can we coalesce? And the quick answer is we cannot, right? If they're not accessing the same address, then we cannot. We cannot coalesce here. So, and not only we cannot coalesce, and if you're considering address translation, we need to do address translation on each access. So we need 64 transactions. Okay. In this case, I will call this is the worst coalesce. Okay, so there's no way for us to coalesce, and we have to generate 64 transactions. And sometimes it can have even more than 64 transactions. In what case? So for example, the last one is right at, so let's say your address is something plus 60, okay? This is a cache line starting address. So you want to read this particular address, and you want to read 8 byte. Okay? So even one thread, the last thread, may go across 2 cache lines. In this case, you may need to load 65 transactions. That can happen. So your hardware has to handle these cases, right, to generate the right number of transactions. This is definitely the worst performance that you can expect. And we can try to see if we have opportunities to address this problem by carefully writing our program. Okay, so this is coalescing. Then, as you can see, the coalescing can be quite complex. For example, we can have something like this. So here is 1, here is 1, here is 4, here is 64, 16, here is 64. Okay, here then is 16 again, and 8, and so on, right? So in some cases, those addresses can be everywhere. There's no certain stride. So or coalescer has to be able to reorganize or actually sort everything, then try to find opportunities to coalesce. Then sort sounds very easy in high-level programming. And then just imagine if I ask you to write a combinational logic to sort something, how hard it is. It can be really hard. Okay, so the coalescing is not that simple. Earlier GPUs cannot do coalescing at 64 transaction level. So they may probably only do, say, 16 or even 8 threads to coalescing. And the early GPUs can also do something like, we can only consider regular thread. We cannot consider irregular thread. Okay, if we encounter an irregular thread, we'll immediately start a new transaction. Those are early stage coalescers. And today in GPU, I think as far as I know, they have perfect coalescer already. They can do everything just directly in coalescer. But don't expect it can be completed in one cycle. Okay, it may take many, many cycles to perform this operation. Okay. So in GPU, typically when we learn the RISC-V part, the instruction pipeline, the memory is part of the pipeline. Or if you consider L1 cache is there, then L1 cache is the pipeline. So if it's the part of the pipeline, that means the latency is 1 cycle. You have to get the data in 1 cycle. Then we measured the L1 cache latency in R9 Nano GPU, released in 2015. You guess what latency we get? We get 140 cycle latency. L1 cache is 140 level latency. That is something you want to tell others. They won't believe in that. They think this is absurd. No L1 cache should be this high. Then L1 cache can be 5 cycle latency, but it cannot be 140 cycle latency. Then I think other experiment also validated our experiment. Then today, L1 cache for GPU is much faster, but still it's not 5 cycle latency. So in state-of-art AMD and NVIDIA GPUs, you can expect 20 to 30 nanosecond latency. If you consider, like, we don't know what's their frequency, right? If it's 1 gigahertz, it's 20 to 30 cycle latency. If it's 2 gigahertz, it's about 40 to 60 cycle latency. That's still quite a large value for GPUs, right? So I can tell you why R9 Nano is so slow at that time. GPU was originally designed for graphics, right? In graphics, you probably heard of this term called pyramid. Do you know what's a pyramid? Pyramid? In plain English context. Egypt pyramid, right? So what is a pyramid in the graphics context? Is in this way. So you have a texture image, right? It's your texture image. Then if on the screen is very far away, you don't really need full resolution image. You can use lower resolution. So there's an image with half resolution, 1/4 of resolution, 1/8 of the resolution, right? GPU allows you to specify, okay, I want this one at this location. Then the hardware will automatically determine how far away it is and which level we need to use and recalculate the address to get the equivalent pixel. Okay? So think about how complex this operation is. These are all built into the pipeline. Then this is all built into the pipeline, which makes the vector memory unit, the addressing part, the address calculation, super complex. And by that time, 2015, even before 2015, GPU, general purpose GPU, is not a very popular thing yet, right? When it's not a very popular thing, these things are in the instruction pipeline itself. Okay, in this pipeline. So it's very, very complex and very slow. And because it's very slow, then later on when GPU is becoming more and more important, these two parts separate. If you really need this pyramid operation, you go to pyramid part. Right? If you don't need pyramid, just do the quick coalescing. Then coalescing may take like 10 cycles, for example. Then that's why it can significantly reduce the latency from something like 140 cycles down to like 20 to 30 cycles. Not only pyramid, there are a lot of very complex things that are on graphics specific, that are being splitted from the pipeline and to make it more graphics specific in the GPU architecture. Okay, this is vector memory unit. Then vector memory unit, assuming we have the memory transaction generated, now we need to start to look at the memory hierarchy, or the L1 caches, L2 caches. Let's talk about that. Now when we talk about that, we don't need this figure anymore. We need to look at the whole GPU level. Look at the whole GPU level. We still start with a compute unit. Okay. Then each compute unit will have one L1V cache. Then you're super familiar with V already. It's for vector cache, right? So 4 CUs when joining 4 of them is this also called a shader array. By the way, a CU in the graphics concept is also called a shader. Why is a shader? What is a shader? Shader is a multi-used term. So in graphics, a shader means something that can calculate the color of something, right? It can be either a hardware or a program. Sometimes you write a shader program. Sometimes it just refers to a hardware that can do the calculation. So CU is also called a shader, and for CUs is called a shader array. Okay, when we have something like a term that describes a group of something, we have some resources, hardware resources that are shared. In this case, what are shared? We have one extra cache that's called L1S. Then you have V, you have S, right? Shader, scalar, and vector. Then we have another cache that's called L1I cache, instruction cache. Okay, so these are shared by compute unit. By every 4 compute unit. Okay. So why they are likely to be shared? So you need to know instruction shared. That's very common, right? So shaders are helping each other. If one shader loads the address here, then all other 4 when one CU loads the instruction, the other 3 instructions, the other 3 CUs will already have it to reduce the hit rate, reduce the miss rate. Scalar is also the same idea. So scalar, what does scalar memory do? So by the way, scalar memory is responsible by the scalar unit. It can also generate some load, like a read and write request into L1S. No write, only read. So this is a read only. This is a read only. And I'm writing this is a read only. It's actually not exactly a read only, but you can consider it a read only. Like why we need to write into instruction cache, right? But it's not important. Just consider this is a read only cache. So these are read only cache, and L1S is responsible for calculating addresses, loading some like kernel arguments, some launch parameters like what's the block size, what's the kernel size, these things that are will not change, right? So every program, every thread will need that part of information. Every thread needs that part of information and will not change. So it's better to be shared. Okay, so that's why they are shared. And L1 cache is also larger, right? So another question is, a very common question is also in CPU. When you have a data cache and the instruction cache, then someone may ask you, interviewer may ask you, why they need 2 caches? Then the always right answer is they have different locality. They have different access pattern, right? For example, this one we are very likely to hit, then the cache hit rate here is actually quite low. Okay. But anyway, those are the L1 caches and L2 caches, okay? Then in R9 Nano GPU, we have 16 SAs, right? We have 16 shader array, and that makes 64 compute unit, okay? Then on the other side, we have L2 caches. There are several of them, okay? So how many? I don't exactly remember the number, and is either between 8 to 16. Okay, there are this number of L2 caches. And there are some memory controllers. Let's just make it simple. Each L2 is connecting to one memory controller. I'm writing DRAM. DRAM. And DRAM. Okay. So why we want to design in this way is because those are directly connected. Because we want to maximize the throughput. We want to maximize the bandwidth from the memory. So we want to pump data as fast as possible to the core side. Remember, in CPU, we may have like a few cores, 64 cores at most, right? Then how much data that we can load? Not much. And how much data we can load on the GPU side? We can easily load like thousands of threads at the same time. They're all pumping data to the GPUs, to the core. So we really need high bandwidth. The way to provide high bandwidth is to provide high parallelism, right? So that these DRAMs can provide data as quick as possible. Okay, so how we can make it as quick as possible? We design in this way. We ask them, we allocate the address range in an interleaved way. So let's say if this has the address of 60 to 127, okay, there either two cache line, two 64-byte cache line, or one 128-byte cache line. Then this one will have address of 128 to 255, okay, and so on. Then it go back to here. And if there are 8, then it go back to 2K to 2K plus 128, 27. 2K plus 128 to 2K plus 255. Okay, so this is interleaving. Because you want to load a lot of data, you want to load a lot of data, and the probability of loading into each bank of these L2 caches are likely to be the same. We can evenly distribute the load to all these banks. Okay, we can evenly distribute all this load to all these banks so that they can provide the data at the same time to maximize the bandwidth. Okay, now let me ask a quick question. What's the address range for each L1 cache? So this has an address range, right? Although we can keep writing this, but there is an address range. What's the address range for L1 cache? 0 to 2K. No, why 2K?
I think that for the full run of each memory controller.
Yeah. So we didn't say how large the memory is the GPU, right? So
because we have 16 L2 cache.
Mm.
Like each L2 cache can serve 127, 128. We have 16 L2 caches, and like we also have the 60 L2 caches can run at the same time. We only need to support 2K memory address in L2 cache.
So let me tell you the answer here. So it's basically from 0 to infinity, right? So the core wants some address. We have to provide that address, right? The core can ask any address it wants as long as it's within the range of the whole GPU. It's not bounded by 2K. Like think about today DRAM, they're easily 40 gigabytes, right?
To be concrete, I think that 0 to 2K because they have a 4-week cache or this kind. I mean, to have them to map to different set.
Yeah. So to here, the thing is these L1 caches are not mapped to address range. They have to cover. So whatever the data that this CU wants to access, it has to be able to provide that. So basically, there's no certain range. It needs to cover everything that this CU wants. Okay, so it needs to cover everything it wants. So all of them will have 0 to infinity, 0 to infinity, and so on. Okay, so what do we call this type of cache? We call this core side cache. And this side, you may already guess the name, right? We call this side memory side cache. These are memory side cache because each L2 is only responsible for 1 DRAM. These are memory side cache, and these are core side cache. For core side cache, we have to cover the whole address range. No matter what the core wants, we have to be able to cache that. For memory side, it's okay. We only cover the address range that this DRAM controller is working on. Okay. So then the question is, if there's a port here, which L2 it needs to connect to? All of them, right? So because it needs to access all the addresses. And this one needs to access to all of the addresses. This one needs to access all the addresses, and so on. How many clients are there? I mean, how many clients of the L2 caches are there? It's basically calculated by 16 multiplied by 6, right? Equals to 96. So 6, right? 6 L1 caches. Multiplied by 16, there are 96 L1 caches. So what's happening is there's a huge network. We call it interconnect. Or if you want to know the technology here, in most of GPUs, this is done by a crossbar. Okay, crossbar. Like people typically write X bar, but crossbar is CROSS bar. Okay, it's a big network that is connecting all the L1 caches and all the L2 caches. Okay, and this crossbar in a GPU takes a lot of energy and also die size. Then that's only 16 shader arrays, right? Think about the future generations of GPUs. Then MI100 has 120 compute units. These are only 64 CUs, 120. Then like something at H100, I don't really know the number, but it's a quite large number, 200 something, right? Is this crossbar still scalable? We call this a scalability problem. We call this a state scalability problem because as we keep adding more compute units and more L2 caches, this one crossbar cannot hold. Now what can they do? What they actually do in NVIDIA GPUs is partition. So we don't provide one big crossbar. We generate 2 crossbars, right? And we generate a connection between these 2 crossbars to reduce their wires, reduce the number of wires. We connect them together. And this connects to their own L2 caches. Okay. Then there's some L2 caches. It really depends on the design. If we also want to partition the L1 side or not, we can do or do not. Like let's assume we do partition L1 side, okay? So they say if this part needs to access this part of the L1 cache needs to access this part of L2 cache. By the way, these two, I want to draw a new one. This is becoming complex. It's becoming complex. So let's say this is one L1 cache. There are two, just make it simple, two L1 caches. Two L1 caches, okay? And this is a crossbar network. And this is one network. And this is L2, 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 L2. Okay, so we have two partitions. Then there's still many design decisions. For example, here we can assume that this L2 this two L2 needs to hold address from 0 to infinity, although we can interleave within them. Then these L2s can have 0 to infinity, right? Okay. That means this part only need to access this part, and that part only need to access that part, right? Shouldn't draw this here in this case. Then, but in the memory, we only have one set of memory, right? We only have one set of memory. We only have one set of memory, so we cannot allow a piece of data to be stored in two memory. That's too expensive. We only have 40 gigabytes of memory, and we want to maximize them. So here's the memory. The memory controllers. Okay, let me draw 6 of them. So that means we need another crossbar at this point, so that, say, this one may connect to, just make it simpler, draw 4 of them. This one may connect to these two. This one may connect to these two. This one connects to this one and this one. And this one connects to this one and the third. Okay. So we're actually, then compare this crossbar. It's several hundred by several hundred input, tens of output. This one is a few input and a few output. So the crossbar here, the complexity is significantly lower than a big crossbar there. Okay. That's what NVIDIA GPU is doing. I don't know if recent AMD GPU is doing this or not, but this can reduce the scalability of the problem. But definitely at a cost that if you are accessing from one part to another part, then the latency penalty is higher. It's not as, the performance is not as high. They're very unlikely they use a crossbar here, but they use some sort of switch that if you need to access that part of memory, then they actually need this thing to, so they probably do something like this. So there's another wire here, right? If you need to access that partition, you need to go multiple hops to go to the destination. So latency is higher in NVIDIA GPUs. Okay, then let's see, we have 10 more minutes. See if we can finish this part or not. Coherency issue. Then what is coherency issue? Let's make it simple. L2 cache, L1 cache, L1 cache, right? So if this is cache line A, and here we're loading cache line A, and we read cache line A, both read are okay, right? And they say they're version 1. Version 1. This originally has version 1, but then we do a write. It has version 2. Okay, A2 here. What if after that one is doing A2, we do a read? We're reading A1 here. Although, by the way, if this is a write, remember GPU L1 cache are all write-through cache. We don't say it's a write-through or write-around, but it's a write-through family. Okay? So A1 will also go here, but this one, if we don't have careful consideration, this one will still have A1. Right? This one still have A1. So what can we do? How we can solve this problem? We broadcast the write request, right? So think about how large our GPU is. How many cores are there? Hundreds of cores. So then it's a scalability issue. Right? For CPUs, we can do that. For GPUs, can we also do that? Then the quick answer is the GPU wants to be as simple as possible. So we only do the useful part. We discard the non-useful part. So how GPU solve this problem? GPU tells programmer, this is wrong. Don't write this type of program. Okay? So you should never write one piece of data and expect the other side to load it in the one kernel. If you load it, it can be old data. If you load old data, don't blame anyone. That's the problem of your program. Okay? So this is something called programmer controlled coherency. So there was actually a very interesting discussion at the Micro last year in the conference. So was the keynote speaker was saying that, then was Todd Austin, who was a speaker here last week, right? So he asked a question about some architecture. I don't exactly remember what's the architecture. He was asking, so why we are so just tweak our hardware that much to follow the habit of the programmer. So why we not write something like in GPUs? Just don't do this. This is not good. This is not good for performance. Just don't do this. Right? So, well, I think that's a very reasonable consideration. Now, if we want high performance, we have to have some constraints. So just programmer, don't write this type of program. Then what if you really need another thread to read the data? How you can do that? At a barrier is not good enough. Barrier is a consistent issue, it's complex, but it will still have this one here. So atomic can work. Atomic can broadcast and force eviction of other kernels. But atomic, if you use too much atomic, it's a performance penalty, right? The right answer is to stop the kernel, start a new one. Okay, just stop the kernel and start a new one. The new one will load it from the memory. So at the kernel boundary, we need to flush a one cache. Not really flush. We actually only need to invalid in a one cache. Right? So from a V state, from valid state to a invalid state. Okay, we only need to do a V to I conversion. Okay. So just mark all the cache lines are invalid. Then at the beginning of the next kernel, just load everything back, because after that we already have everything, all the up-to-date data in L2 cache. If we really need to write somewhere from one thread and load from another thread, write them in two different kernels. So GPUs encourage you to somehow write simple kernels and to say, if this is a matrix multiplication, then only write a matrix multiplication. Don't combine other things here. And it also encourages you to say, each thread will only have a certain addresses that you want to write into, right? So don't try to have two threads write into one part, or one thread write here, then the other thread read from here. Don't do that. It's not something that you should do in a GPU program. And So many people eventually will still ask this question, how GPU is handling this type of coherency. And the quick question is GPU doesn't, and GPU doesn't care. And it's the programmer's responsibility to do that. Just one thing. It's a certain term that I should talk in the cache coherency, the regular lecture of cache coherency that I was planning to give today. Then it's a fact called false sharing. Okay, what is false sharing? False sharing is like this. Oh, it's larger. This is L2 cache. Then this is a cache line. This is L1 cache. Then for this L1 cache, we only need to write into this part, right? Then for this L1 cache, we only need to write into the second half. This is totally legitimate. No problem at all, right? Because programmers shouldn't really know which part of data, which byte are in one cache line. But in hardware, you have to consider this type of situation. So let's say, if you write through, then this type of write through, this first write through, this second write through, right? What will happen is, let's say this is A2 and this is A3, then this is A1, right? Ideally, we wanted to have A2 and A3. But if we don't do anything, what will happen into A1, A3? Because here is A1. Here is A1. A1, the second half of A1. Okay? How we can solve this problem? Just imagine you are the GPU designer, how we can solve this problem. I'm giving an oversimplified example that we're writing half of a cache line. It can be small. It can be 1 byte, 2 byte, 4 byte, and so on. Okay, I don't think we have time. I will tell you the answer. Okay, so other than data, we carry something called a write mask. Which part we want to write. And this write mask is 1 bit for 4 byte. Okay? 1 bit for 4 byte. So we mark which part is 30. And when we write, say, okay, this part we want to write. And when it's combined, okay, we only update that part. Then it can merge at this part and have A2 and A3. Just a corner case, if you really have one instruction to write 1 byte, what happens is to do a write evict. Or the write evict is the easiest way to do. If you only need to write 1 byte. 1 byte cannot be represented by this, right? Just write down here and write the whole cache line here. Because this one should already happen, right? This is write through. This already happened. If you only want to run 1 byte, then don't have write mask. Just write the whole data there. Okay, so immediately write there and evict from here. Then you don't have this type of coherency problem. This is called false sharing because you feel you are sharing this cache line, but in the program you only need part of the cache line. It's not real sharing.